So now let's come to our last attempt number 3. And as I say, third time the charm. This better work out. So Dirac was aware of the problem of the Klein-Gordon equation and the problem for the square root operator. So what he proposed was that he proposed a wave equation which will be first order in time. So he wrote down a wave equation, I h bar del psi by del t, and that's equal to minus I h bar c alpha, which is a triplet of matrices, dotted with the gradient operator and acting on psi plus mc squared, another matrix called beta acting on psi. So the price that Dirac paid was that he promoted the wave function psi to matrix wave function. So Dirac assumed, well, he was looking for an equation for the electron. So initially he thought that the matrix wave function will have two components, say psi1 and psi2. But as we shall see, that does not work. So the other thing is that you may know this is that a first order wave equation is not compatible with the homogeneity of spacetime. So first order, if you didn't have matrices here, if this was just a plain first order equation, you could show that that equation can only give you solution that goes to the left or solutions that go to the right. It doesn't give you solutions which go both ways. So, but of course, this is not our usual first order wave equation. This has matrices in it. What are the properties of these matrices? Okay, before we go to that, let's just like scratch this out because this is not true. So what Dirac assumed is that psi was a matrix, so it has a matrix index A. So this is not a spacetime index. This is some other index A, and then alpha is it's a triplet of matrices. So let's call it, say, alpha 1, alpha 2, and alpha 3, or let's just actually use alpha 1 downstairs, alpha 2, alpha 3. And alpha acting on our, alpha acting on the wave function is again a column matrix, and this is given by alpha BC acting on C. Note that these indices, these labels 1, 2, 3. Sorry, the eraser just comes on automatically. These labels 1, 2, 3 are not these indices. These are labels, whereas these indices are indices of the whatever by whatever matrix. Similarly, we have beta acting on psi is a matrix element A of a column matrix, and beta is given by AB acting on psi. Right. So let's look at the Dirac Hamiltonian more closely. So the Dirac Hamiltonian is C times alpha dot, say, so suppose that it acts on some momentum eigenfunction. If it acts on the momentum eigenfunction, then the momentum operator will just become the momentum P, and then we have mc squared times P. Now, if I square, like in the Klein-Gordon case, the Dirac Hamiltonian, what do I get? I get C squared, and then I get alpha I, alpha j, and alpha I is contracted with, say, pi, and alpha j with pj. So these are two factors of momentum. And then we'll have a cross term, which is mc cubed, and then we at p of So let's put these indices upstairs. This is upstairs, and this is P upstairs I, and then we have alpha I beta plus beta alpha I. Remember that beta and alpha are matrices, so they don't commute in general, plus m squared c to the power 4 beta squared. Now, of course, this is the square of the energy, and we know what the square of the energy is. It's given by p squared c squared plus m squared c to the power 4. So our expectation is this should be equal to p squared c squared plus m squared c to the power 4. But that is only going to happen if these matrices satisfy certain condition. So what are those conditions? So to see that, let's rewrite h squared. Now see that these are just numbers, so they commute. So this part of the first term is symmetric in INJ. And therefore, we can rewrite the first term as c squared, a commutator of alpha I, alpha j times half of pi pj. So what we have done here is that we have taken this term, multiplied by 2 and divided by half, and then we have written the two terms separately and then relabeled the indices in one of those terms and written this as an anti-commutator. And the second term we can write as mc cubed p of I, an anti-commutator of alpha I beta, and the third term, we just leave it as it is. So thus we see that this relationship gives us the squared relativistic mass energy condition if the commutator of alpha I and alpha j is equal to 2 delta ij, and alpha I, the three matrices, anti-commute with beta. By the way, the anti-commutator of AB is defined as AB plus BA. And B squared is 1. So if these three conditions are satisfied, then we see that this thing gives the relativistic mass energy condition. So Dirac adopted these conditions. So these conditions and this equation, along with those three conditions, is called the Dirac equation. And the Dirac equation is an equation which is consistent both with special relativity as well as quantum mechanics. So one thing to note is that because the Dirac equation is first order in time, the probability density that you derive from the Dirac equation is actually a positive definite quantity. Of course, to compute that, you have to take the Hermitian conjugate because in the Dirac equation, the wave function is a matrix wave function. The Dirac equation is a relativistic equation. However, it's neither a scalar equation nor a tensor equation. It involves a new kind of objects which are called spinors, and spinors are needed to describe fermions. So when we discuss spinors and fermions later in the course, we shall explicitly show the relativistic invariance of the Dirac equation. So the Dirac equation involves four matrices. 3 alpha I matrices and 1 beta matrix. And they all anti-commute. So Dirac's initial plan, or his aim, was that he wanted to derive an equation for the electron. And because the electron is a spin half particle, you'd expect that these matrices, the wave functions, will be a two-component column vector, and therefore these alpha and beta matrices would be 2 by 2 matrices. But there's a problem there. In 2 dimensions, there are only 3 matrices which anti-commute with each other, and these are the well-known Pauli matrices. It's easy to show that any matrix which there are no other matrix which anti-commutes with the Pauli matrices, which is also 2 by 2 dimensions. If you don't know what the Pauli matrices are, let me remind you, or let me tell you what they are. Sigma 1 is 0, 1, 1. On the off diagonal, sigma 2 is 0, 0 on the diagonal and minus I on the off diagonal, and sigma 3 is 1 and minus 1 along the diagonal and 0, 0 on the off diagonal. Now, what Dirac found was that the lowest dimension in which he could find 4 matrices which satisfy the Dirac algebra are the following matrices. He took alpha I to be, along the diagonal, he took the Paulis, and then beta is along the diagonal, you had 2 by 2 zero matrices, and on the off diagonal, you get an identity matrix. And you can verify that alpha I and beta, given the Pauli matrix relationship, that they satisfy the Dirac algebra.